Good afternoon, everyone. We will revise what we discussed in the previous lecture, which was Monte Carlo sampling. We will see some more use cases of Monte Carlo sampling. Are there any questions? Okay. We saw this previously, that we are trying to find out integrals of the form fx, px, dx. Importantly, px here is a distribution. Fx is any function you wish to compute on it. And then you're trying to figure out this expectation or the integration, right? So the typical way in which such methods are being employed in the course in the context of Bayesian machine learning is, we'll have Px to be what? The prior or the posterior, Fx to be the likelihood. Right, that's generally the way which we'll be using fx to be some likelihood like function and px to be some probability distribution. Most of the times we'll be using things like the prior or the posterior. And we say that we can replace this expectation or the integration via a summation as 1 over n summation f of xi, importantly where xi is drawn from px. Right, so in today's lecture we'll look at how to draw samples from a probability distribution. Thus far, we've been using torch.distributions.something.sample or np.random.randn or rand. So we've been drawing samples through that. Today, we want to see how to get samples from any given distribution. We saw how to calculate the value of pi using Monte Carlo methods. So for value of pi, what is fx and what is px that we can use? Let's look at the figure. Right, so just look at the figure. This is what we're trying to get. We're saying that the samples which are within this region of x1 squared plus x2 squared less than equal to 1, their area divided by the total area will be equal to the ratio of pi by 4. Right? So we start with this diagram as the representative picture, and what is the fx and px that we want to be using for this example. So if you remember the square that we saw, what is the size of the square? 0, 0, 2, 0, 1 and 1, 0 and 1, 1. So that are the 4 extremes of the square. You are trying to uniformly or you are trying to randomly get a dot or a point on that square. What distribution can we use? A uniform distribution in what dimension? In 2D space, right? And we want a function which gives you a green if the value is within the circle and it gives you a red when it's outside the circle. So this kind of function has to be something like an if-else function. Right? Now you could write an if-else function or you could write it as an indicator function. Both of them you can write equivalently, and therefore with this particular fx chosen and this particular px, we'd be able to get pi by 4 value. We saw this last time also. So in the last discussion, we also saw that this leads to an estimate. I said it's an unbiased estimate, but there is a lot of variance in it. I'll not go over all of the proof for this. I will just show you the notebook again. Right, so this is what we're trying to do. We had this function which generated the samples, random uniform samples. It computed the distance. It looked at this function fx, which is an indicator function. So it's just binary function. We looked at the points inside. We found out the sum. We looked at the points outside. We found out the estimate of pi. And then what we did was for different sample sizes, 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, we were generating different number of samples. And we were trying to obtain the estimate of pi for different random seeds. And we get a table like this. For each number of samples n, we have different seeds over which we try, and we obtain a different estimate of pi. And then we just try to group these results and plot them. The true value is shown as 3.14, this horizontal line. We see that the estimates that we are obtaining even for a low value of n, if you average them out, you will get a reasonably good estimate, which is close to 3.2, but the variance is huge. as you increase the value of n, the variance keeps on reducing, and the estimate is anyway supposed to be unbiased estimate. So you would be able to get the correct value. We importantly also saw that if you want to get within a 0.0001 of the true value, you'll need something like 10 to the power 8 samples, right, which is very wasteful for something for which perfect algorithms at this point are known. Right? So therefore, sampling is expensive. We should try and avoid if it's possible, if there are exact methods to do. So this is mainly showing the fact that the estimator that we have is an unbiased estimator, which means that the expectation of phi hat turns out to be phi. I'm just leaving the proof on the slides for later study. And the variance, it's proportional to the number of, inversely proportional to the number of samples. So therefore, you have to increase the number of samples to a large extent in order to get a small error, which is as expected. But using such calculations, and if you're able to figure out some of the constants here, you'd be able to precisely get a sense of how many samples do you need, so that your estimate is within a certain digits of the true value. Right? It will turn out to be a huge number.
What is the current best series for finding the value of phi, like the current most convergent series?
I don't have that at the top of my head, but I can tell you that I had a discussion with various CS faculty on this. So it's a active area. There is so one was the blog which I think we'd shown on the previous discussion also. So this was Tensor, this was Pi Google Cloud, 100 trillion digits of pi on Google Cloud, and they are using this particular algorithm, which is, I believe, the state of the art then. So they ran this algorithm for 157 days on very heavy duty machines. Right. Importantly, they are able to show that, so if you just see the increase in the number of digits that they are able to get, it's very rapid. Right. The important thing is that the main takeaway message from this particular slide is that the estimate is unbiased, but it exhibits variance, and the variance is inversely proportional to the number of samples. So we'd seen till this point and little more beyond, but it's important to again get back the context. And as I was mentioning, we'll be mostly using this in the context of machine learning in this course, which means P of theta or P of x would be the prior or the posterior most of the cases. So we could have had a prior which is normal 0, 1 for each of the I, or we could have had a general P of theta is some normal distribution with a mean mu vector and a covariance matrix sigma, capital sigma. And we can then assume the likelihood function. With the case of linear regression, it's just normal with the mean x transpose theta and with some known scale and known variance. In this case, let's assume it's 1. So we can then compute the prior predictive distribution, right? So this is the distribution in y, given that we don't, given that we have not taken into considerations any samples, right? So P of y given x is integral of P of y given theta x, P theta d theta, and we can write theta I is sampled from P of theta, right? This is just replacing of the integral with the summation. So we saw this last time also, but let's again revise lin-reg predictive. Right, so we put some prior, mean and covariance. We create the prior distribution. In this case, I'm calling it theta. It's a multivariate normal with a certain mean and certain covariance. I can view the multivariate normal distribution over here. I can get some 1000 samples from it. And this is essentially doing what I had mentioned. For different values of x, right, for different value of x, I plug in the sample theta naught into x plus theta 1, sorry, theta naught plus theta 1 into x, right. For corresponding to that, I get a different y linear, right. So I get a different line, and if I plot all of these lines, So these are the different possible y values functions that I can generate, right? Given that I have not observed the data, that is the important thing. This is prior predictive. And if you were to take the mean and the standard deviation, so we'd get a function, we'll get a graphic something like this. We'd also said that we know the closed form for prior predictive distribution, which is something like this. Now this was similar to one of the questions in your exam also. So M naught is the mean of the prior and S naught is the covariance of the prior. Sigma square is the variance, the noise variance, and phi is just the basis function expansion. So in simple terms, it's just 1 in x, and for polynomial it will be 1x, x squared, so on and so forth. So knowing this closed form distribution, we also simulated the same, and we obtained a function which looked exactly the same, right? So our closed form distribution, predictive distribution, importantly again it's predictive, so it's probability of y given x. We brought in, to be able to solve this, we brought in theta and we integrated it out, right? P of y given x is integral of P of y given theta and x times P theta d theta, and that we write it as this summation. Any question in this? So the advantage of MC sampling is that, so for this particular case, for linear regression, we knew this closed form expression, right? If the prior is a normal and the likelihood is also normal, we know that this is the predictive distribution, right? But if the prior is not a normal distribution, we cannot, in general, we cannot obtain such kinds of closed form solutions. So we have to resort to Monte Carlo simulations, and I am showing a particular term here. So this is a mixture of Gaussians, right? We have two multivariate normals. First multivariate normal has 0, 0 mean, and the other one has 3 minus 2 mean, and then there are different covariances. I am adding them in the ratio 0.7 to 0.3, which creates a mixture of Gaussian distribution. So this is the general syntax, Schwarzschild distribution, so mixture, same family. You need to give the categorical distribution corresponding to their ratios, and then the different distributions. I have generated 1000 samples from it. Now you can see this is not the same as the distributions you have been seeing thus far, right? There seems to be some more mass here, lesser mass over here, and that is also reflected in the samples that I am drawing from this. Now the good thing of using Monte Carlo sampling is that I don't need to change anything else in my code. I just replace theta underscore sample equal to theta dot sample or prior dot sample to MOG dot sample. Everything else remains the same. So the likelihood function remains the same. And if I do this, I obtain a slightly different kind of prior predictive distribution, right? So now you can see that there seems to be some specific bias. It's not symmetrical about x equal to 0. It's symmetrical about something like there seems to be a change somewhere else, and there seems to be a downward slope. Whereas for the previous case, we saw that this is parallel to, this is y equal to 0 is the mean. So the mean here is not y equal to 0. Similar to the way we have obtained the prior predictive, we can also obtain the posterior predictive. Right? The only change that we need to do is, instead of using p of theta, we'll have to choose p of theta given d. Okay. So if you remember previously, I had also said that we can also use Monte Carlo sampling to compute the marginal likelihood or the evidence term, right? So in the Bayes rule, we are given 4 terms. P of theta given d is the posterior, P of d given theta is the likelihood, P of theta is the prior, and P of d is the evidence term. What can we write P of d as? Integration of P of likelihood and the prior, right? So that's what exactly we'll do. P of, we have theta to be normally distributed with some mean and covariance. We have the likelihood for a given sample as yn given x and theta is normally distributed with x transpose theta sigma square, which is sigma square is the noise variance. And we want to obtain the marginal likelihood, which is P of D, probability of the data, right? And that is given as, we can also write that as P of y given x. So here we always put this conditioning to show that x was supposed to be known, and then we are trying to see what y we can get based on this x. So P of y given x is this integral of P of y given x and theta, P theta d theta, which we can just plug in the expressions. It's a normal times a normal integral. Right? So nothing new till this point. Again, because we're dealing with normals, we end up getting an expression which is also a normal distribution. So this may seem a little weird. We are trying to find P of y given x. You would expect this to be, you would suppose this to be a constant, right? P of y given x, right? It turns out to be normal with y in the variable y, the mean being x m naught, and this being the covariance, right? You don't need to know all the specifics. I just wanted to show that this is the particular distribution that you'll get, right?
Sir, but till now we assumed it to be a constant.
What to be constant?
The data term.
Mm-hmm.
So now we are getting a distribution.
Okay, so let's go over this entire class, and then if it's still unsolved, we'll talk about it. Right? So P of y given x will turn out to be this particular normal distribution. Right? Now, this was again available in closed form, but generally it will not be available in closed form. Right? So think of the other kinds of distributions where the prior is, let's say, normal distribution and the likelihood is Bernoulli. Right? So that is this logistic regression kind of a setup. There, if you have to compute the denominator term, P of D term, we won't be able to get in such closed form expressions. Therefore, what do we need to do? Monte Carlo sampling. So we could just write this as I equal to P of y given x is approximately equal to 1 over n, and just corresponding to the P of y given x and a particular value theta I, right, where theta I is distributed from the prior distribution. Okay. So now think of this as you want to compute I, but I have to think about writing some code for this. Typically, none of the software libraries give me P of y given x, right? So P of y given x, so the second term that you're seeing, P of y given x and theta I, this is a normal distribution with the variable y, mean x theta, and the variance sigma square I, right? So software libraries typically don't give me the dot prob, they give me log prob, right? So if I have to compute I will typically not be getting this P of y given x comma theta I, it will be getting the log of this term, right? Can I just take an exponentiation of this and get I?
Yes.
Technically, yes, right? But if that were the case, I would not be asking this question. So I think we've gone too little abstract. Let's go into the code and reflect back. So the remaining part of the code, the first part of the code is exactly the same as we'd seen before. We have a prior mu, prior covariance, and we are able to get a prior distribution theta. So the main difference between this notebook, which is I'm calling it the evidence term, and the predictive distribution, where we were looking at the prior predictive, what do you think is the main difference? So both of these problems I am solving using Monte Carlo integration. What is the main difference? So let's go back to the slides. Prior predictive is you want to be predicting the y value at a given x value, or y star at a new x star, which is p of y given theta and x times p theta integral over d theta, with integrated over all thetas, right? Have you considered the data thus far? No, right? This is just prior predictive, and you're trying to just estimate p of y given x, whereas in the new integral that we're trying to solve, there you're trying to compute probability of observing all the data set y's given all the data set x's. Right? Do you see the difference between these two things? In the first case, you're trying to obtain the distribution in y given any x without having observed the data for prior predictive and after observing data for posterior predictive. So it's p of y star given x star, that is the question. Here we are trying to compute what is probability of observing all the data set y's corresponding to all the data set x's. So therefore this will turn out to be two different integrations. Right? But the code, the first part of the code is exactly the same. But here, because we needed the data, so I have generated some data. Right? This is the data, and this is the evidence that you're trying to compute, p of d given theta, p theta, d theta. Right? And we can just write it as 1 over n, p of d theta I, where theta is distributed as prior. We have plotted the prior as we did previously. We have generated the samples as we had done previously, theta dot sample. Our log likelihood function. So importantly, I am now writing the log likelihood function. It's basically just you find theta naught plus theta 1 into x, and you have a normal distribution with that mean and a certain variance, and the log prob over the observations y, and just summing them over. Right? So we've been seeing this for a long time now, this same equation, log likelihood. You find out the mean prediction for any given thetas. You have the log likelihood as a normal distribution with the mean and a certain noise variance, and you find out the log prob over the data. Right? And you sum it up here. So importantly, if we were to consider the log likelihood over the different theta samples, I'm showing it for 3 different values of thetas. The first is any sample that I had drawn from the prior. The second is also another sample which I have drawn from the prior. And the third one is the true value of theta which generated the data. So naturally you would see that the log likelihood is the maximum amongst these 3 at least for the theta which has generated the data, right, which is as expected. And if you look at the different theta values, so the first sample theta is 1 and minus 0.4, and the second one is minus 2 and 0.5. The true theta was 1.5 and 0.5. So we can also see that the first sample was probably a little closer to the true theta compared to the second one. Therefore, the log likelihood is higher. Right? If we were to get some samples corresponding to these different thetas, we again get these lines. Now this is prior predictive, right? But what we're looking for is, okay, before that I also want to show you another thing. I have computed the log likelihoods for 3 different values of theta, and now I am trying to exponentiate them, right? So the log likelihood values are 20.7, minus 595 and minus 1800. If I take the exponentiation of them, I get a very large value for the first theta value, and I get 0 and 0, right? which is effectively telling me that I cannot be computing the log likelihood and taking an exponentiation of that to obtain the likelihood term, right. The likelihood term will simply give me an underflow, right. So, I need to do something better. So, with this context, let us go back to this slide, right. P of y given x comma theta I, we are not able to compute this. Instead, we are able to compute log of P of y given x and theta I, right. But I wanted to compute I, or I wanted to perhaps compute log of I. So, that is a hint. I want, instead of computing I, let me try and compute log of I, right. So, if I have to compute log of I, can I write it as log of I equal to log of this entire thing, which is equivalent to log of 1 over n summation of p to the power y x theta I, right. So, nothing changed. I have just put a logarithmic outside the entire thing, right. Now, I am saying that we should be using something known as the log sum exponential trick. We briefly looked at this trick in the previous course when we were trying to compute the softmax, right, and we had a very hard time without using log sum exponential trick. So, can you now in your notebooks think what you need to do in order to obtain or apply the log sum exponential trick over it? The hint is in the name itself, log sum exponential. So, they have to be in this specific order only. The terms have to be in this order only. I do not want you to figure out the exact mechanics of how to work, but where is exponential occurring, where is the sum occurring, where is the logarithmic occurring, and how would you want to simplify this expression? Yeah. Right. Yeah. 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 Right. Right. Mm-hmm. 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 Okay. Yeah, that is correct. Let's everyone think for 2-3 more minutes and then we'll discuss this. Importantly, you want to figure out where the log is in this expression, where the sum is, and where the exponentiation is. The exponentiation is probably the only thing which is not particularly clear in this. Just as an aside, I was trying to work out this example today morning for the lecture, and I thought this should just take 2 minutes. I thought this would be a very easy integration like the prior predictive, but this turned out to be much harder just because of these numerical issues. Okay, let's first go back and look at the log sum exponential trick in the general form, and then we'll come back to our specific case, and then we'll look at the code for solving this problem. Right. So, the log sum exponential trick is you're trying to compute log sum over exponents, right? And this you'd see that this occurs in when you're trying to compute the softmax like things, right? So log sum exponentiation. You can just write this as log over, you figure out the maximum a of I, right? And then you subtract that from these terms and you take it outside, e to the power max of ai, right? That will make these calculations better conditioned. So logarithmic of e to the power max I is just max of I. You don't need to compute e to the power max I, right? So even if maximum value of ai is a large value, you never have to compute that. Just because of the simplification you get that. And then you have certain other terms in this expression. Right? So bringing it back to our particular problem, we can write logarithmic of 1 over n summation p of y given x and theta I to be e to the power log likelihood. Right? The log prob or the log likelihood we already know, and we have an e to the power log likelihood term. Right? So nothing has changed. We've just written it in the, we've just written e to the power log likelihood. And then we can also figure out the maximum of the likelihood, log likelihood term, and then just do a bit of manipulation to do this. So in my code, I will not require this manipulation myself, but I will be using Torch's inbuilt log sum exponential trick implementation. So let me now go back to the code. So I am now looking at, is the size visible? Should I make it slightly big? Okay. So I am using 12,000 samples. I am looking at, I am storing all the log likelihood values corresponding to each sample. So each sample means each sample of theta, right? So for I in range n, I generate a theta sample, or I could have just generated the n samples in one go, but I am just doing this to keep it simple. I generate a sample of theta. I compute the log likelihood, right? This is the same log likelihood function you've been using in your course thus far. And I just put these values into this empty list, into this list for now. And this is how I use the trick. So I have log marginal likelihood equal to minus torch.log n plus torch.log sum exponentiation of the log likelihood values. Right? Internally log sum exponentiation will give you the correct values. You don't need to worry about that. Right? So what we're saying is that these are log likelihood values, right? You will have to exponentiate them, right? You take a sum over them and then you're finally computing a log over that. And then you also had a log of divided by n term from the Monte Carlo estimate. So that comes in as minus torch log n. If I run this for some number of samples, so I am presently getting 11.2-ish some value, and as I had mentioned from looking at this, we know the true distribution also, we know the denominator term also here, right? P of y given x is normal distribution in y given mean x m naught, and this is the covariance, right? So we can compute x to be like this. We calculate the sigma square term. We have the sigma square term. We calculate the capital matrix x. We find out the prior covariance. We take an inverse, and we can then just write it in this form, right? Torch's distribution is a multivariate normal. So x into m naught, plus we write multiply x prior covariance x transpose plus sigma squared into I. So plus sigma squared into I into x into s transpose into s naught into x transpose. So x into s naught into x transpose. We don't need this term. So it's the marginal likelihood term, which we've written as a distribution, and we then trying to find out the log probability of observing y. right? It's a multivariate normal distribution with 100 cross 100 covariance and 100 mean values. And if you look at the log prob of the data, turns out to be 12.3, not very far from the log marginal likelihood that we evaluated here. Right? Again, for some different samples, we ended up getting something closer value. For some reason, I've been requiring a lot more samples in this particular code as opposed to for my other examples. So perhaps there's some small bug you can figure out at some point. But this was the important thing, that this is fortunately for us available in the closed form, right? And we are now able to see the same calculation using Monte Carlo estimation. Again, it's requiring a lot of samples, and then also it's not super accurate, right? So wherever possible, if you have the closed form, just use that. But in general, we will not require the computation of such terms, P of t terms, right? We just make smarter assumptions, like we use the Laplace approximation, which is a Gaussian approximation. We don't care about computing the denominator. We can just work with the anomalized density there, right? We just look at the log of joint, and we're able to compute the approximate log posterior, and various other techniques we also don't require to compute P of t. Right? So that is what I was saying. I was expecting this integration to be a very simple one. It turned out to be much more complicated. It's still not fully resolved at this point. Any questions? Okay, I think we have done all the hard work for today's lecture for now. We'll now have something fairly simple things. So thus far we've been assuming we have a way to sample from the normal distribution, right? But what if we don't know how to sample from a normal distribution? If you had to write your own library to sample from a normal distribution, sample from a uniform distribution, how do you think you might do that? The first thing we'll want to do is to start off with uniform distribution, right? How can you get a random uniform number between 0 and 1? Okay, we have very few people. I can ask. Okay, Suraj, what do you think? How can we get a random uniform number between 0 and 1? Anyone, any guesses? Okay, we can't get random, we can get pseudo-random. Okay, how can we get something which is as per a pseudo-random number generation algorithm between 0 and 1? Gaurav, what do you think? You can take a C value or seed value, okay. Okay. So what Gaurav is saying is fairly similar to an algorithm that I have, but you had a different answer perhaps.
Like taking a process from nature that is truly random.
Okay. What might that be? Let's say them out. So Utkarsh says that pseudo random number generators are way too pseudo. They're not random number generators. Perhaps we should take something which is truly random. What might that be? Sorry? Inverse CDF. We'll come to that pretty late, but as of now we're looking at, so inverse CDF uses uniform distribution. Here the question is to generate a uniform distribution. Uniform. Okay, Kush, what do you think? Okay.
Sir, one way to get a very close to random process is to just measure the distance of the user's pointer.
Okay.
And
Okay.
maybe we have the max distance already recorded.
Right. So what Ritik is saying is that because you want something between 0 and 1, you can get some bounds, right, of some screen, and he's perhaps saying in a 1D space wherever mouse pointer is. So let's say this indicates a 0 and this indicates a 1, right? Something like that, and that you can do that in a 2D space also. All of them you can do, but typically you will not look for that. Those things are very, very slow because you're looking at some input output. You want to be generating numbers very quickly. So have you studied the topic PRNGs in algorithms or any other course? Pseudo number generators? Okay. Okay. So we look at one particular algorithm called linear congruential generator, LCGs. Python uses a similar algorithm that's called Mercian twister. Right? But for many of these things, we'll be looking at the Wikipedia articles only. So this is the main algorithm. I want everyone to just note this down, this particular expression, and then we'll just want to solve it and ensure that we're able to get correct numbers. X of n plus 1 equal to a times xn plus c, the whole modulus m. And this is saying that x naught is the seed, right? This is where you see the seed in your libraries when you specify random numbers. So x naught is the seed, a, c and m are some constants which would be dependent on the algorithm, various things. Sometimes you'll choose some of them based on like prime numbers, etc. X of n plus 1 is the next random number, right? If everyone has just written down this formula.
Is there something between mod and the previous expression?
So this entire thing modulus m, a xn plus c modulus m. This has been copied from Wikipedia, therefore it looks like this. Yes, it's like a clock. So let's work this out. If we look at the first figure, seed equal to 1, right? M equal to 9, which means we are looking modulus 9. So we'll be having numbers from 0 through 8, right? A equal to 2 and C equal to 0. So our algorithm is A into x n plus C modulus m. So our A is 2, x naught is 1. So 2 into 1 plus 0 modulus 9. So from 1 we multiply that with 2, we get 2. 2 modulus 9 is 2. So therefore the next one is 2. The first number is 2. Now x of 1 is 2. You multiply that with 2, you will get 4. 4 modulus 9 is 4. 4 into 2 is 8. 8 modulus 9 is 8. 8 into 2 is 16. 16 modulus 9 is 7. 7 into 2 is 14. Modulus 9 is 5. 5 into 2 is 10. Modulus 9 is 1. Now at this point, do you see that the cycle will repeat? Right? The cycle will repeat. So therefore, we have generated a sequence after only 1, 2, 3, 4, 5, 6, 7 numbers or 6 numbers, we'll start having repetitions. So this particular cycle is very, very small. So therefore, we'll be looking at numbers m, a and c, which make the cycle bigger. If we had chosen m equal to 9, a equal to 2, c equal to 0, and we start with a different seed here, right, the cycle is smaller, right? So that's where the seed also becomes dependent. So typically you'll want to choose an algorithm values of m, a and c, so that whatever seed you give, the cycle is very, very long, right? And this is how you're able to get reproducibility results. So now you have defined the source of randomness. But here you're getting numbers between 0 to 8. This is not what you wanted. You wanted a random uniform number between 0 and 1. How do you transform this? Whatever number you get through this, you divide by 9, right? So seems like a very simple algorithm, but this seems to work well. Now if you look at some code for the same, they can be, but you just don't want cycles to occur very often, right? So I'll show the ranges of numbers we take. So it's called random uniform. So the typical numbers that we take, right? So we are taking a to be this huge number, c to be a huge number, and m to be 2 to the power 32, right? Again, why have we chosen these numbers? I don't know. I picked them up. Right? So I think a course in crypto will give you more information on this. And please let me know also once you figured out all the details. But this is where you want to be looking at prime numbers, 2 to the power modular exponentiation, and that's where. So I believe you would have studied modular exponentiation algorithms in your DSA 1 or DSA 2 algorithm courses. But this is where you actually are able to use these, right? So effectively, the algorithm here is just A into seed plus seed modulus m, and then I'm just dividing it by m. For generating n numbers, I'm just running a loop over this. So I call it simple PRNG. I pass in the seed. I generate some 10,000 numbers, and if I plot a histogram of them, they are between 0 and 1 as expected as a sanity check, and it seems to be fairly uniform. Right? I can also plot the KDE plot for this, and it seems to be working fine. Kernel density estimation, it's as expected. If we were to instead use numpy.random.rand, so numpy is random uniform generator, the histogram is fairly similar, and so is the KDE plot. Right, so it seems that we've been able to get uniform distribution samples, or samples from uniform distribution between 0 and 1. Right. Questions on this? How, sorry? I don't know the exact reasons or the mathematical proof behind this, but I think visually it seems to be, if you look at the cycles, right, you'll be, if we had these large numbers, you'd end up picking roughly approximately equally from all the numbers. I don't know the exact mathematical proof of this. There was another question, same question. Okay. Yes, Ritik.
So if our goal is to not let values repeat, wouldn't we want m to be very large and as n plus c term to be very small, so that
I think firstly we are okay with values repeating, especially because it's pseudo random number generation. It's not exact random number generation. We are okay with that. And we pick up these specific values. I don't know the exact reason. It works out okay. So this is a counter example of what not to pick. Right? In this case, you pick a particular seed and you're stuck with that. You want to at least choose algorithms where, independent of the seed, you're able to see wide range of values, right? Almost all the values. So this was generating between 0 and 1. How can we generate samples from uniform A to B? What do we need to do? Yes. Slightly louder. Okay. Yes. So if we have to generate samples from A to B, and we assume that we already have samples from 0 to 1, we can say the new random variable y, which is distributed as uniform A to B, you can get it as A plus B minus A into X is distributed as a uniform A to B. Right? This is a fairly well known result, and I just verified the same through code also. So if I change A and B to something, and I can just apply this transformation, and then I'll get something similar, right? So therefore, most of the times whenever you're implementing these algorithms, you want to be implementing uniform 0 to 1, and then you can get anything, any uniform A to B range. Right? Okay, so thus far we have established how to get samples from the uniform distribution, and it seems that we are able to do that. Right? But uniform is a very, very trivial distribution. We want to be now using the uniform distribution as a starting point and generate samples from some more complicated distributions. Right. One particular method is called inverse CDF sampling. So before looking at the specific of the method, let's just look at the exponential distribution for which we'll try and get some samples. The PDF of the exponential is given as lambda e to the power minus lambda x, and the CDF is given as fx equal to 1 minus e to the power minus lambda x. We know the CDF, we can calculate it analytically. So this is the PDF. So firstly, you're defining it in the non-negative range. You're not having any density in the negative range, and this is the exponential, and this is the CDF. So can you just take 2 minutes and verify that the CDF is this only in your notebook? Can you do this integration? So while I have already given you the result, this is important because you then understand that how inverse CDF method works. You have to be able to compute the CDF given any PDF. How many are able to solve this? Okay. But you see, it's not as easy as you thought, perhaps. It takes a bit of time. Okay. I think the only tricky thing is to remember the formula for CDF and just not get confused with the limits, not do the calculation wrongly. So fx, the CDF is the integration of the PDF from minus infinity to a particular value x naught, whichever way you want to put it, and that I've just shown through 3 different steps. It turns out to be 1 minus e to the power minus lambda x. What is the range of CDF? It varies from what to what? 0 to 1, right? We already know how to sample from the uniform distribution between 0 and 1. And this is the link now we are trying to establish. So we know how to sample from uniform 0 to 1. We know that the CDF of any distribution is 0 to 1. Right? So that's what we'll do now. So let's consider the CDF of the exponential distribution, and I've put a very specific value of lambda equal to 1. Right? I want to be able to generate samples from this particular PDF, which is exponential with lambda equal to 1, and I can analytically find out the CDF for this. Right. So let's generate a random uniform number from uniform distribution between 0 and 1. Right. Here it turns out to be something like 0.9. Right. I take that 0.9, I map it to the CDF, see where it cuts the CDF function, correspondingly find the x corresponding to that value, right? So I take the value, I find out the inverse of the CDF at that value, right? U generated between 0 and 1, corresponding to the value of u, I find out the inverse of the CDF function. Right? The inverse of the CDF function is x. The CDF function goes from x to CDF, x to a value between 0 and 1. We are trying to do the reverse. We start from the value between 0 and 1, and we are trying to map that to the value of x. Therefore, it's the inverse of the CDF function which you are trying to compute. We can take another value. So in this case, it turns out to be 0.95 or so, and correspondingly the x is higher. Right? We can repeat this procedure multiple times, and you'll see that the random uniform number will be between 0 and 1. right? So I've now generated about 9 samples from the uniform distribution. I've mapped each of the sample to the CDF, found out the corresponding sample in X, right? What we're saying is that if you look at these samples that you're obtaining by finding out the inverse of the CDF are distributed as per the distribution of interest, which is the exponential distribution, right? So let's perhaps take a look at the code and see first whether we are doing it correctly or not. Right. So I have the exponential distribution, the true distribution from which I am trying to generate the samples. I don't know how to generate samples, let's assume. I look over some ranges of values, and this is the true PDF, exponential distribution dot log prob of x dot exponentiation, right? I'm computing the PDF over a range of values. I am generating random numbers. Sorry, I'm generating these. So I am generating these random numbers from the uniform distribution. I take the exponential distribution. I compute the inverse CDF for the uniformly distributed numbers I've generated, right? So here I know the exponent dot ICDF function, which is given by the PyTorch library, but otherwise also we have computed it analytically. It's 1 minus e to the power minus lambda x. So we could have just done that also, right? And just put the value u there. And we are looking at the samples generated through the different methods. One is the true PDF, and the other is the KD using inverse CDF method. And we can see that all of them are coinciding, right? Which is showing that we've been able to correctly get the samples from the exponential distribution, right? In this case, again, we had access to the sampling from this distribution, but we are assuming that we didn't have, or who knows, internally PyTorch could be using something like inverse CDF method to compute the samples from the exponential distribution. I want to just leave you with the quick proof, that the intuition of the proof which Wikipedia article gives. So we have u, which is uniform between 0 and 1. We want to generate x with CDF fx, and we want fx to be continuously increasing, etc., etc. So what we're saying is that let's assume a transformation which exists, which takes you from 0 to 1 to any real number, such that when you apply the transformation on the uniformly generated numbers, that gives you the x, right? So we start with that. We know the definition of PDF, which is x less than equal to x value. We can substitute x to be t of u, and we can apply the inverse on both sides. So t of u less than equal to x is same as probability of u less than equal to t inverse of x, and it's a monotonically increasing function. So we're able to do these things. Probability of u less than equal to t inverse of x equal to t inverse of x. How can we write this? So let me ask a simpler question. What is the probability that a randomly uniform number generated between 0 and 1 would be less than 0.5? Just 0.5. Just 0.5, right? So that's the definition of the uniform distribution. Probability that the random variable is generated is less than y is just y. Right? So therefore, this is the broad intuition for inverse CDF sampling. It's a nice method if you're able to get the CDFs, right? But are we able to compute the CDF for many distributions? Not for all, right? It's not trivial to compute the CDF for all. Do we know the CDF for the normal distribution? Yes.
Not exactly. There is an error.
So the CDF is defined in terms of some error function, which is itself not easy to compute. Right? For many distributions, the CDFs may not be very easy to compute. If we can't compute the CDF, we can't compute the inverse CDF also. Right? So we have generated uniform numbers. We can say that for any distribution for which we can find out the CDF trivially, we can use inverse CDF method. It's a decent method. For many distributions, we can't compute the CDFs, including normal distribution. Like we can technically still use some code and get that, but it's not trivial to use that. And because normal distribution itself very ubiquitous in the domain, so let's use some standard methods to generate samples from normal distribution. Right? We'll be using the method known as box-Muller transform to generate samples from normal 0 to 1, 0, 1. So this interestingly makes use of the uniform distribution. So again, now we have all the tools to be able to generate this. We start with generating uniform random variables, 2 uniform random variables, and we want to generate 2 independent random variables Z0 and Z1. So there are these few formulas that are given. Right? We can, for now, let's directly use these specific formulas, or we can just go to the Wikipedia page of box-Muller transformation. Right? It gives a bit of visualization, it gives the basic form, but essentially the idea is that once you have uniform distribution, the samples from a uniform distribution, you can obtain samples from normal distribution with mean 0, variance 1. Right? This is best, I think, just shown directly in the code without right. So essentially we need to do something like this. You generate samples from the uniform distribution, you figure out the r and theta, and then you write x equal to r cos theta and y equal to r sin theta. And through this, we are able to get the true density of the normal distribution, which you already know. And we're looking at the PDF for samples, KD plot corresponding to samples x and y, 2 distributions. Right. So through this procedure, we're able to get 2 random variables, 2 normal distributions, samples from 2 normal distributions, x and y. Right. Or if you just wanted 1, you could have just used n over 2 if you want n samples from the normal distribution, and then just concatenate them. So once we get samples from 0, 1, can you tell me how to get samples from normal mu with mean mu and variance sigma square? For uniform distribution, it was a plus b minus a into samples from uniform 0 to 1. What transformation do you need to take? Given normal 0, 1 samples, you want to get samples from normal mu and sigma. Does anyone remember this? So it's again a simple transformation, mu plus sigma times Z0. Right? You might have again already seen this transformation earlier in some courses. So if Z is normal 0, 1 random variable, then x, which is mu plus sigma times Z, is the random variable with mean, mu and variance sigma square. Right. So therefore, if you see now, we are incrementally building all the tools. We know how to get samples from uniform distribution. Using uniform distribution, if we know the CDF of any distribution, we can figure out through inverse CDF sampling We can get the samples from any particular distribution whose CDF we know. We said that the normal distribution is a very important distribution, so we can also get samples from normal 0, 1. If we get samples from normal 0, 1, we can also get samples from normal mu and sigma, right, through this simple transformation. If we know samples from normal 0, 1, we can also get samples from normal multivariate normal with mu and capital sigma. How do you think this will happen? So we know how to get samples from normal 0, 1. We know how to get samples from normal mu and sigma, univariate case. How can we get samples from mu and covariance matrix? Sorry? Yeah. So if we wanted to get samples from univariate normal with mean mu and variance sigma square, how did we get that? First, find out samples from the standard normal, right? And then you did some transformation. So the idea for multivariate normal is similar. You first get samples from multivariate normal with mean 0 and covariance. What is the equivalent of variance 1 in the multivariate case? Identity matrix, right? You get samples from normal with mean 0 vector and the covariance to be the identity matrix. Now what do you do after that? So univariate case, this is the transformation, mu plus sigma z. What is the transformation for multivariate case? The important thing here is that you can think of sigma to be the square root of variance, right? But there we don't have the variance term, we have the covariance term, right? We need an equivalent of the covariance term, which is the Cholesky decomposition. Right? Again, we might not have heard of this, or we might have studied it in some course, but not actively reflected on it. So we'll again go back to just the distribution, multivariate normal distribution, and this drawing values. So we want something which is equivalent of the square root of the covariance matrix, right? So there's sigma. So univariate case, sigma is the square root of the variance. Here's the Cholesky decomposition of the matrix, the covariance matrix. So we can say that for any real matrix A, such that A into A transpose is the covariance, right? You can think of it as the square root. Right? This is known as the Cholesky decomposition. Once we find out the square root like term, we can then put mu equal to A, mu plus AZ to obtain samples from this multivariate normal, right? How do we get samples from multivariate normal with mean 0 and covariance identity? How can we get that? So let everyone think for a second. How do we get samples from multivariate normal distribution with mean 0 vector and covariance as the identity matrix?
Get a lot of samples, we get like what if the dimension is n, then get n samples from normal 0, 1.
Yeah, right. So when the covariance is identity, it means that the different sub-random vectors have nothing in common, right? They are not correlated with each other, which means that you might as well as just generate each dimension. x1 is normally distributed 0, 1, x2 is normally distributed 0, 1, so on and so forth. If you do that, you will be able to generate capital X, which is the random vector x1, x through xn, which is normally distributed with the mean 0 and covariance identity matrix. And then once you have the covariance matrix, you can find out the Cholesky decomposition and then add it up. So if we go back to the code, so if the true mean is 1 minus 1 and the true covariance is 1, 0.5, 0.5 and 1, the true distribution is multivariate normal with true mean and true covariance. We are able to get samples using torch We want to see if our samples which we get using our distribution would be similar or not. So I get, let's say 4,000 samples using this true distribution, and I plot the joint plot. The covariance matrix is expected, right? So this is the KD plot, the density is as expected because of this covariance term 0.5. So x and y are positively correlated, and it seems that the mean is 1 and minus 1. So the mean is 1 and minus 1, right? And then you have these contour lines around that. This is the samples, this KD plot for the samples generated from the true distribution. But instead now let's find out the equivalent of the square root of the covariance matrix, which is known as the Cholesky decomposition. So L equal to torch or Cholesky of the true covariance. This gives you a matrix 1, 0, 0.5 and 0.86. So it gives you a lower triangular matrix. So that's the equivalent of square root. You can verify that L into L transpose gives you the original covariance matrix. Right. And now all I'm saying is that we have generated some samples from the univariate normal distribution earlier. Right. X I generated from the univariate normal distribution, or in fact I'd use the Box-Miller transform to get some samples X and get some samples Y, both univariate normals. I can just put them as Zi equal to, and just stack them up, and then the random variable, which is the multivariate normal, I want to get samples for that. So I do Zi into L transpose plus true mean, which is equivalent to what we saw in Wikipedia, mu plus A times Z. A is the Cholesky decomposition of the covariance matrix. Z is the random variable corresponding to multivariate normal distribution with mean, mu, 0 vector and covariance identity matrix. Mu is the mean of the multivariate normal which you're trying to sample from. And if we plot the density plot for the samples that we have generated, it seems that they're quite matching the samples which we got from torch implementation. So some of these details, I think they'll be best understood once you're able to go through the notebook and generate some things like this on your own. Okay, I think I'd prefer not to start rejection sampling because I see that we're a bit tired today. So we can skip that for the next lecture. That's a much more interesting algorithm, rejection sampling. Today's lecture was a bit more mathematical initially, and then the second part I think was a little easy. So thus far what we've seen is that in today's lecture we saw that Monte Carlo integration requires you to compute, is giving you the approximation of fx px dx, integration of that, but that requires you to sample from p of x. For the purposes of this course, mostly we'll be looking at prior predictive like terms, posterior predictive like terms, or some similar terms, or the evidence term. But then that naturally begs the question that how do we sample from p of x? Right? Now, thus far we've been using torch, but let's imagine if torch didn't exist, or if we had to implement those algorithms from scratch, what might we do? We looked at first the simple case of uniform distribution. We said that we can use some pseudo random number generator like linear congruential generator, or something like Mersenne twister which Python uses, and based on that we can get uniform between 0 and 1. Once we have uniform between 0 and 1, we can get uniform between A and B. Once we have uniform between 0 and 1, we can also use the inverse CDF sampler. So for inverse CDF sampler, we start with a PDF, we analytically find out the CDF, and we need to know the inverse of this function, right? In this case, it's quite easy because of some simple algorithms which exist, but not for all the cases. So in fact, I think I forgot to show those specific slides. Right, I forgot to show this. So for the exponential distribution, when we're trying to compute samples by the inverse CDF method, we generate a random number u given as u01, and we are saying that small u is equal to 1 minus e to the power minus x, right? This is a CDF, right? Now we can just invert, take x on the other side, get x equal to minus log of 1 minus u, right? So this is the inverse CDF function which we are trying to compute. Starts with u, gives you the x. The CDF function starts with x, gives you the CDF of x, right? So now all you need to do is to generate random uniform numbers 0, 1 and put in this formula. You will get samples from the corresponding distribution. The important thing is that here all of these things were easily calculatable, and the CDF was easily analytically available. The inverse CDF was also easy to calculate, but for many distributions that might not be the case, including the normal distribution, which meant that we need to have certain better ways of drawing samples from the normal distribution. We looked at the simple case of normal distribution, standard normal 0, 1. We are able to get samples through that, through the Box-Miller transform. Once we have normal 0, 1, we can get samples from normal mu sigma using the transformation mu plus sigma times z. Once we have samples from normal 0, 1, we can also get samples from multivariate normal with mean, zero vector and covariance matrix identity. And once we have that, we can get samples from any multivariate normal distribution. So we'll end at this point. In the next class, we look at an algorithm called rejection sampling, which will be slightly easier and it will make a lot more sense rather than some of these very specific tools for finding out the distribution. And right, that's it. So apart from this, I think there was a couple of